In the last lecture, I introduced you to this theorem. You have two angles, alpha and beta, and as long as their sum is not an integer multiple of 2 pi, then if I do two rotations, one about some point A by alpha, another one about some point B by beta, then the product of the rotations is a rotation about some point C by alpha plus beta. If alpha plus beta is an integer multiple of 2 pi, we get the product of these two rotations is a translation. So now I want to give you an example of how to use that theorem. You'll see a number of examples I've written up in the notes, examples on translations and rotations, and I'm doing the fourth one first just to give you some idea of the power of this theorem. So you can read what this says on your own by looking at that PDF file on my website, but let me go ahead and just show you with a picture what it's saying. So we're starting with an arbitrary triangle, it can be any triangle, and we're going to put equilateral triangles off the edges, so exterior to the given triangle. So we have an equilateral triangle here, an equilateral triangle here, and an equilateral triangle here. And then we want to take the centers of these equilateral triangles. Well, what's the center? For an equilateral triangle, just anything works. You can take the intersection of the angle bisectors, you can take the intersection of the perpendicular bisectors, you can take the intersection of the altitudes. They're all the same. So we want the center of these equilateral triangles. And then what we want to do is to connect these centers to get a triangle. And the example we're doing is to show that no matter what triangle we started with, this blue triangle in the middle here, what we end up with when we do these centers is an equilateral triangle. So independent of what the first triangle is, we drew these equilateral triangles off the sides and connected them by their centers, and we got an equilateral triangle. So we want to prove that happens all the time. So let's go through the proof. Now, the hard part of the proof might be to figure out how to get started here. And I'm going to do this, and after we've had practice on a few, I think it'll become easier for you. So what we're going to look at is the rotation about C prime by 2 pi over 3, where C prime was the center of this equilateral triangle, followed by a rotation about B prime by 2 pi over 3, the center of this equilateral triangle, followed by a rotation about A prime by 2 pi over 3, around this point of this triangle. Okay, so we want to do those three rotations. If you look at what happens to B, I first want to rotate about C prime by 2 pi over 3. Again, we're going counterclockwise. So if I go counterclockwise, 2 pi over 3, what's 2 pi over 3? Notice the angles in the middle here are all 2 pi over 3. There's 3 of them. Going all the way around is 2 pi. So from here to here to here, this angle is 2 pi over 3. This was the center of this equilateral triangle. These distances will be the same. So B is just going to go to A when I rotate about C prime by 2 pi over 3. So B will go to A. And now I want to rotate around B prime by 2 pi over 3. Again, this distance and this distance will be the same, and this angle will be 2 pi over 3. So A is just going to go to C. And then I want to rotate about A prime by 2 pi over 3. And so again, C is just going to go to B. So we see that if I take f of b, if I apply b to this function, it just ends up back at b. So b goes to A goes to C, and then C goes to B. So what does that mean about this function? Well, it sounds like maybe this b is the center of our rotation that we talked about earlier, but that's not what's going on with this function, because if you look at the sum of these three angles, it's 2 pi. And so when we have a multiple of 2 pi, f is going to be a translation. So we're going to move everything in the plane in a certain direction, a certain amount. And we want to go from B to B. Wait a minute, if you're translating and you're just going from B to B, what does that mean? Well, if we're going the same direction, the same amount for all points, that means we're going nowhere. B is going to be You're translating by 0, 0. You're not moving. So really, this is just the identity, and everything stays where it's at. Although that would happen if you considered this a rotation by 2 pi about b, you would end up back where you were. That is not the way you want to think about this, because in general, doesn't necessarily equal the identity function. It just happens to be identity function in this case because b went to b. So we think of it being the identity function because we know it's a translation, and b goes to b. So everything has to go to itself. The next point I want to look at is c prime. If I rotate about c prime by 2 pi over 3, I'm going to end up at c prime. So that's an easy thing to try to look at. So c prime, when I rotate everything around c prime by 2 pi over 3, c prime doesn't move. So c prime gets sent to itself under the first rotation. Under the next rotation about b prime by 2 pi over 3, well, I'm not sure where it's going. I'll just give it a name, and I'll call that c double prime. Okay, so c double prime is the result of rotating c prime around b prime by 2 pi over 3. So it looks like it's over here someplace because I'm rotating counterclockwise by 2 pi over 3. But what we know is f of c prime has to be c prime. So I have to end up back at c prime. So first this c prime goes to c prime, then c prime goes to c double prime, and now it has to go back to c prime because f is the identity function. So wherever c double prime is over here, it has to go after rotation through a prime back at c prime. So a little thought here, the picture looks something like this. I've rotated about b prime, c prime here, and so it goes here. These two distances have to be the same because it's a rotation about b prime. And then I take this and I rotate about a prime, and so this distance has to be this distance because I'm rotating about a prime here, and I'm ending up at c prime. Okay, so we rotate about c prime, end up here, rotate about a prime, we end up back here. Okay, well, that tells us some information. These two sides are equal again in length. These two sides are equal in length. This side's equal to itself. So that means these two triangles, this one here and this one here, have to be congruent. Again, this side is equal to this side is equal to this side is equal to itself. So triangle A prime, B prime, C prime is congruent to triangle A prime, B prime, C double prime. What does that mean? Well, this angle was 120 degrees, 2 pi over 3. And since these two triangles are congruent, these two angles have to be the same. So each of them have to be 60. Similarly here, this was 120 degrees, this rotation. Both these angles are the same because we have congruent triangles here. So they're both 60 degrees. So we get that those two angles are 60 degrees. This one and this one. Well, of course, the third angle of the triangle has to also be 60 degrees because the sum of the angles of a triangle add up to 180 degrees. So we have an equilateral triangle here like we were trying to prove. These angles are all 60 degrees. So the result is then that A prime, B prime, C prime is in fact an equilateral triangle, and that proves what we were trying to prove. Let me comment that the fifth example, which I'm not going to go through in detail, is telling you that there's a more general result that's true. And let me give you a picture of what that is. Again, we start with any triangle. Now, rather than putting equilateral triangles off the sides, exterior to this triangle, I'm going to draw any triangle. So absolutely any triangle off of one of these sides. And what I want to do is take this triangle and put it on each of these sides as well, but I've used the second longest length of an edge here for this triangle. I want to use each of these edges once. I've used this one now. So now I want to take the shortest edge and use it someplace, and the longest edge and use it someplace, and use those on these sides. So for example, here's the smallest edge, this one being used off the side of this edge here. And again, it's not the same size because I'm trying to draw something that's similar, but all the angles are the same. So all the angles are the same. So it's a similar triangle to this triangle. but here I've used the smallest edge. The one edge I haven't used so far is the longest edge, so I want to use that here. And if I use the longest edge there, I get this triangle. Again, it's obviously not the same size, but it's similar to the other two triangles that we drew here. The angles are the same, and here I put the longest edge here. So I've used each of the edges once in a sense, because they're the longest one, the shortest one, and the middle one are all used once. And these are all similar triangles. And so now what we want to do is define some kind of point that they have in common, like the center of the equilateral triangles. And for that, what you use is actually the perpendicular bisectors of the sides. So I take the perpendicular bisectors of the sides, and I get a point. We showed before that if you take the perpendicular bisectors of all three sides, they go through the same point. So just take any two sides, take where they intersect, and that will give you a point. And do that for each of these triangles that are exterior to the triangle we started with. And finally, I want to do it for this triangle. And the point is there. So this is the perpendicular bisector of this side. This is the perpendicular bisector of this side. They intersect here. So now we connect these three new points we've found. And you can see what happens. The result is that we get a triangle that's similar to the triangle we had on the outside here. So if these were all equilateral triangles, a triangle similar to that would be an equilateral triangle as well. But if they're not, it still works. You get something different than an equilateral triangle then. So that's a generalization of the theorem we just talked about.